On face value, a 1965 Ford Mustang might not be the most obvious choice for time attack style road racing. However, we're here with Mike from Dusold Designs to find out why we can make one of these cars compete with and sometimes beat more modern technology. So first of all, Mike, what actually drove you to choose a 65 Mustang as the basis for this build?
So my friend Mark brought this car to our shop years ago on a pallet where it was like a roof and he had cut all the rusty parts off and didn't really have much left. And he originally was going to have a street car. And then as we were building it, I was developing my Camaro and he got hooked and I let him drive it a couple times. And then he decided, I want one of those too. And he wanted to be able to do a car that he could drive on the street, take out to dinner, but also go really fast on the track and have fun at time attack style events and have a car that's really multi-purpose.
Okay, well the car obviously is a work of art, and while, as you've mentioned to me off camera, it's a fresh build, hasn't really seen a lot of competition, it definitely looks like it's got the runs on the board to get the job done. Let's start with analysing the base 65 Mustang. Where are the shortcomings in terms of getting it to be effective as a road race vehicle?
So the first thing that's a big problem with the 65 Mustang is the suspension geometry back in 65 was not intended for handling. These things were intended to drive people back and forth to work, go on dirt roads, and back then the speed limit was 55 miles an hour, so speed was not a thing. So the first thing that we had to upgrade with the car was the suspension. So in the front, we decided to go with the Detroit Speed Alumiframe style front suspension, and that gives us a short long arm with much more modern geometry, rack and pinion steering. We've got a real high quality JRI coilover shock on there and really improved that geometry a ton so that we can get better camber gain, better roll center height, things like that just weren't a consideration with the original suspension design.
Generally just geometry that is more suited to a road race application rather than just a garden variety pedestrian car.
Yeah, and it's really kind of a shift in technology overall in car manufacture entirely. Like the early cars didn't run much caster. They didn't run camber gain at all. They had camber loss and they had really weird roll center heights and the geometry just wasn't built for performance. And now everybody drives these modern cars and they're used to what modern suspension geometry feels like. If they get in an old car, they're like, what is this garbage? It feels like I'm driving a wagon. So you got to upgrade that, get it to more modern specs. And then once you get it there, put on some sticky tires, some good shocks, stiffen it up. It's a whole lot of fun on the road course.
And there's no doubt that technology and geometry targets have moved along since 1965. Obviously, these cars are incredibly popular for those restoring, building, hot rods, basically anything you can imagine. Does this mean that you don't have to go and reinvent the wheel when you want to do these upgrades? A lot of parts availability off the shelf for them?
Yes, there's a lot of parts available for this platform, and this build is kind of that way. It started off where we used a lot of commercially available parts and then just kind of tuned them and tweaked them to get the performance that we wanted. But they're a really great platform. People love the styling of them. They just look really cool. And one advantage that they really do have is that they're light. Like these cars are not hard to keep, 2,800 to 3,200 pounds. When you compare that to a modern Mustang that's like 4,200 pounds. So
yeah, that weight's a definite deficit that you're starting with the later model cars, and of course very difficult and expensive to get that weight out. Just continuing with the chassis for a moment, talk us through what's been done in the rear end of the car.
The rear of this car is a solid axle that has been modified to run a full floating setup with about 1.5 degrees of negative camber. And then it runs a torque arm, which allows us to kind of adjust the instant center and get it to put the power down the way we want. And then it has a Watts link for the lateral location. And then the Watts link also allows us to adjust the rear roll center height.
Okay, so there's a bunch of stuff that I want to talk about there. For a start, you mentioned negative camber, which for most people in a live rear end, a solid axle rear end, that's usually reasonably hard to achieve. So what are the components that allow you to actually add negative camber in this live rear end?
So that uses a Speedway Engineering housing, and they have the ability to actually weld the stubs on the ends of the housing at an angle. And when they do that, you could pick whatever camber you want, and they'll also allow you to choose some toe. So if you want to run just a little bit of toe in, you can, and then they weld it onto whatever your spec is, and it'll run a particular axle where the splines on the end of the axle are actually curved so that the axle can tolerate the misalignment with the hub.
Okay, so no need for an actual constant velocity joint or anything, and I'm guessing you're only running a small amount of camber as well.
Yeah, it's only 1.5 degrees, so we're able to get that with just the axle having a little bit of curvature to it so that it can move. It does make it a wear item, so the axles will wear out over time, but with the simplicity of the system, it's worth it versus having to go to any kind of a joint or something in there that could be another failure point.
Now, I'm guessing here, I haven't had a lot of experience with camber on live rear-end cars, but I'm guessing you wouldn't need the amount of negative camber that you would if it was independent, because essentially the axle is always flat on the ground. You're more taking into account the amount of tyre distortion during body roll or during hard cornering?
Yeah, we're trying to take into account what the tire's going to do as it's moving dynamically in a corner, because it's going to try and lose camber and wear the shoulder of the tire out, and it won't utilize the whole tire. But by adding that little bit of camber, it gives you a significant upgrade in the grip laterally through corners.
All right, let's talk about the lateral location, and that term simply means how the housing, how the whole differential is essentially located side to side in the car. So, I mean, a lot of original live rear-end cars would have been located with a Panhard rod. Can you talk to us about the pros and cons of a Panhard rod versus a Watts linkage?
So the Watts linkage doesn't travel through an arc the same way that a Panhard rod does. So you're going to get some lateral displacement in a Panhard rod no matter what, because it's 2 points, it moves around an arc. The Watts link does not, because it has enough arcs that they cancel each other out with the propeller in the center so that it moves truly vertically. The negative of the Watts link is that they can create some strange jacking moments, and we've had to kind of deal with that with this car. So it'll make you kind of have to play around with your rear roll stiffness, and also, you know, how you do the sway bar and what you do for the rear roll center height to kind of counteract the jacking moments of the Watts link. So there's really not a true better way to go. And if you could argue with chassis engineers till you're blue in the face, and some of them are Watts link guys and some of them are Panhard rod guys, and there's really not a right answer there.
You could probably get comparable results with either. It's not a black and white thing, but just wanted to point out there the Watts linkage, one of the advantages is that you get no lateral movement. It's also more complex to design, to build, and to install. Let's talk about that roll center height that you've mentioned here again. And I mean, it's difficult here without the benefit of some graphics, but essentially it's an imaginary point for the front and rear axle lines that the car is going to roll about when you're in a corner. Now, what's the importance of that roll center height, and what's the importance of being able to adjust it higher or lower?
So the roll center height basically tells you how much you're going to load the inside versus the outside tire when you're traveling through a corner. And it also is how much resistance the car has to roll. So if you raise the roll center height, the car is more resistant to roll, and it will load the inside tire slightly more, but it doesn't load the outside tire as much. So by lowering the roll center heights, we can actually see an improvement in how we feel the grip is. But you need to be very careful with the roll axis, which is the comparison imaginary line between the front and rear roll center heights. So on a car like this, if you get that rear roll center too high, the car will continually want to like jump on the outside front tire. So we have to get that rear roll center low enough that the car will engage the rear tires the way we want. The solid axles tend to be kind of pushy, so people will kind of adjust that rear roll center a little bit higher to kind of disengage the inside rear tire, which will allow the car to turn a little bit more easily. But by disengaging that inside rear tire, you also have the negative effect of you're not going to get to put as much power down on the exit until the car kind of settles back down. So roll center heights are kind of a thing that we use as a tuning tool quite often in cars like this. And once you get it right, you kind of leave it. But it's very difficult to just do math and figure the car on paper before the build and have it right. So that's one of the things that you like to have adjustment on, so that once the car is actually out in the wild, you're driving it, feeling what it's doing, you can make corrections to it and look at the data and tell what it wants.
Okay. These points that we've talked about, these imaginary points, when we've got the ability to actually graph out the suspension components where they are in space. It's not very difficult. This isn't rocket science to actually find out where your roll center heights are and your roll center axis front to rear. When you are developing this car, are you using any software for that process? Are you doing it by hand, or how's that dealt with?
So I usually use Performance Trends. It's kind of a basic software, but it does a really good job of just giving us the data that we want. And then when we go to design the components, we'll move it into Fusion or something like that and put all the points where we want them and design the structures from there. But it really doesn't have to be the world's craziest software. The most difficult part of figuring it all out is actually doing the measuring, because you have to figure out how to get datum points to measure from, and that's the trickiest thing. But once you do that, it'll tell you a lot, and you can also look in some of those things at models of different cars that are existing. One of the cool things that I had was Performance Trends kind of offered a C5 Corvette as this is what that has. And you kind of look at it and play with it and move all the stuff in the model, and it shows you, well, okay, if a Corvette does this and I want to do this a little different, kind of gives you a starting point.
Again, we've mentioned that the car is a relatively fresh build. Have you actually had enough of a chance to shake this down to sort of validate the numbers you found originally and see how everything stacked up on paper in the real world?
Yeah, we have done some testing with it, not significant enough to say that we're happy with it or we think that it's, finalized. But we have made some adjustments to the torque arm, lowering the front torque arm mount. And we've played around with the rear roll center height and the rear roll stiffness, trying to get it to do what we want to do. Because there are, trade-offs with every adjustment. There is no free lunch where you just turn a screw and everything gets better. You trade one thing for another. So that's when I lean on my chassis engineer friend, Scott, and he gives me all kinds of data points, and it's a lot of fun. I really enjoy the conversations and the tuning, because you kind of go, okay, well, let's try this and see what happens. Currently the way the car is set up right now, it's a little bit too soft in the front. We're getting a little bit too much roll across the front axle, so that'll probably be one of the next things we work on. And it might need a little bit more front sway bar. So all of those things are the little fine-tuning adjustments that we'll do to get them just perfect.
I think a lot of people, when they're designing a suspension setup, think that there's these magic numbers, and once we've got those numbers plugged in, that all of the components, that we're good to go. But I sort of liken it to less black and white and more just a whole lot of shades of grey, and it's finding where you want to be in that operational window that suits you and the racetrack. The other element, I think, which is important, is you want to really have some flexibility and tunability in it, so that once you actually get to the track, you can start dialing these elements in to suit. Now, moving on, we can't really go past the engine combination here. So what are you running?
All right, I'm really proud of the fact that this does not have an LS engine in it. Everybody thinks with this build that we just used an LS, and we did not.
That would definitely have the Ford fanatics offside straight from the get-go.
So the Ford guys can be on our side, because it does run a 351 Windsor-based 430-inch small block Ford. Push rod motor. It runs a Ford Motorsport block, and then it runs trick flow heads with the really large exhaust port. Because one of the things that held back the small block Ford forever was they just have a really small exhaust port. Limits what you can do with the exhaust flow, and especially with a big motor like this, with as much power as it's going to produce, we needed that really large exhaust port to be able to handle it. So this thing makes tons of power. It's a fantastic combination, and I got to tell you, the way that Windsor motor sounds is just something else. I just love the way this motor sounds and runs, and we've done some initial testing on it, and at only 8 pounds of boost, with the timing kind of held back, it's 820 at the wheels, and we're going to tune it up to about 1100 at the wheels. But the tricky part that we have is keeping the tires on the dyno, because it's got a lot of torque really early, so as soon as you go into a pull, it wants to spin. So we've got to get around that and tune it up, but it makes tons and tons of power, lots of torque, really nice motor to drive.
In terms of, I don't want to get too controversial on the Ford versus GM, but we've talked about another one of your cars and filmed on that as well, which is LS based. The LS, obviously a newer generation of engine completely. If you were to compare the small block Ford versus an LS similar capacity, if you're talking cubic inch per cubic inch, what's the sort of power difference between the two?
Both architectures were designed by the same guy, believe it or not. So the person that designed the Windsor left Ford and designed the LS for GM. So they're very, very similar. The cylinder head is the main difference, in my opinion. The two cars make very similar power. The LS head is a little bit better. It's got a better valve angle to it than what we can get with the Ford head. But they're both functionally limitless because around that 1,000, 1,100 horsepower mark, we aren't able to really utilize the power for what we're doing very well. So we just kind of build them to make that amount of power and go. The LS is probably a little bit more efficient. It's a little bit simpler and easier to build and cheaper to build than the Ford is. But I feel like with the right cylinder head, the Ford has a lot of potential to be just as good for what we're doing. It takes boost well, probably a little bit torqueier motor out of the Ford. The LS is a little less torque, but I mean, we're splitting hairs. But the Ford sounds better, I think.
Okay, well, there's some pros and cons for both sides of the fence, no matter whether you're a Ford or a GM lover. I mean, I think what you mentioned there as well, the cylinder head really, in terms of engine performance, is the key element. The bottom end there is sort of primarily there to support and hold that power, but the airflow in and out of the head's really going to be the key element. Of course, there is also the turbo package to consider here. So what are the turbos that you're using?
So this car runs two G35-900 Garret turbos, and they really spool fantastically well on it. We control them with the Turbosmart E-gates, and we have a beta firmware motec in there that allows us to control the wastegates individually. So one of the really trick things that we're able to do with those E-gates is it allows us to hold the gates open when the motor's at idle up to the torque peak. So once it starts building torque, then we'll close the gates. And we just kind of happened upon that fact that we were able to make more torque down low with the motor with the gates open. And now it's kind of our strategy. So it was kind of a neat thing that we found.
So you're holding the wastegates completely open up until a point where the engine is going to essentially start spooling the turbos. Is that right?
Correct, and it makes more torque there. And then once we get to that part in the torque curve, then we start closing the wastegates, spool the turbos, and then open them again. And we saw a significant, like 10% or 15% improvement in torque at low RPMs by doing that.
Okay, I'm struggling off the bat to get my head around the process, why that's occurring. Have you got sort of your own understanding of it?
Like I understand. It decreases the exhaust pressure. It bleeds all the exhaust pressure so that we get a little bit better pressure differential in the engine at lower RPM, so the motor just is happier and makes more torque. And then once it's starting to make power, it's able to tolerate that loss of pressure differential and spools the turbo and then makes all the magic happen. But it was really not something we thought would work. But again, we were experimenting, saw it happen, and we're like, this strategy actually works.
Double down on it. All right, other than that, are there any other complexities or advantages with using the electronic wastegates over a conventional pneumatic wastegate?
The one nice thing about the electronic wastegate is that you get really consistent positioning. So when you're targeting the boost with a pneumatic system, most of them you're just targeting a duty cycle and you have a resultant boost pressure, but you don't know if it's consistent as far as positioning. Where with the electronic gates, it's a little bit of a different strategy. You're targeting an actual position of the valve, and it's pretty consistent. And because the PID algorithm is controlling position instead of a pressure, we have less latency and more accuracy with the electric valve.
So you are assuming always a direct relationship at a given RPM between wastegate position and boost, though?
Correct. Yeah, you still assume that, but you also have the ability to know that we're going to have less latency. We don't have to wait for the pneumatic system to work and catch up, because that's like a big spring, really. The electronic motor with just the worm gear, it'll move exactly where we want it really quickly.
One of the problems with these wastegates is the current draw. Well, one of the reasons I think why the uptake has been a little bit slower is that the current draw is excessive for a lot of the ECUs that run a Supersteel 1.0 connector. Essentially, it'll pull up to 20 amps and you're about 8 amps, give or take, on one of those individual terminals. So how are you running this? You mentioned development firmware here from Motec. Is this through an external box, or are you doubled up on half-bridge outputs? How's it work?
Yeah, it's got dual half-bridge controllers. And then what we've done is we've found that really the current draw isn't that bad until you fully stroke it and get to a stop. So once we were able to accurately find the stops in the system and keep it from going to over travel, then we don't see that gigantic spike in amp load, and it's a lot easier on the system. But
I can imagine that current draw would only be for milliseconds at the most anyway if you're trying to do a big movement, and once it's actually in the control zone, it's only going to be moving smaller, so the current draw will be relatively insignificant. Is that a fair assumption?
Yeah, the current draw hasn't been any kind of an issue with it so far. We have had people that are friends of ours that have had difficulty with them. I've kind of likened it to being a problem with that over travel, because it's like an old power window system where they just put a circuit breaker on it when it reached the limit, and when it overamped, it just popped the breaker, and that was how they turned off. And these do the same things. Like before we fully figured out how to get it to not over travel, it would like pop the fuse every time we moved it. And then we figured out, well, it's just because it's overamping when it reaches overcycle. So if we could keep it in the sweet spot, then the amp draw is significantly lower.
So it's just really all about understanding the system you're working with, the limitations and the requirements, and working within those.
Yeah, and this is a new thing for us. This is the first car we've run with the electronic gates. Tim Witteridge, that works with us on a lot of our electronics, thought it was the absolute bee's knees and really wanted to play with it. And it's like, this is the future of, because he had worked with it on some other, factory type e-gate systems, and he said it was just phenomenal with the accuracy that you could get, and you can have really good control really quickly. So that's why we incorporated it here. It's definitely going to be a little bit of a learning curve, but once we got everything figured out, it works really, really well, and they're very accurate now. Like you tell it where you want it to go, and it goes there very quickly, and it's the exact same spot every time.
Yeah, perfect. I mean, it makes a lot of sense. Obviously, a lot of the OEs have, in recent times, moved across to electronic wastegates as well. So I think it's safe to say we're going to see more and more moves away from conventional pneumatic gates. Look, Mike, I want to respect your time, so we'll leave it there. Great to get a bit of a tour of this car. It is an absolute work of art and a credit to everyone involved. So thank you for sharing with us.
Thanks a lot for having us. Always fun to talk to you.
If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.